Welcome back. Continuing our conversation in section 4.1, we're going to now move forward with trying to understand how different angles, even if they're all written in radians, can actually be representing the same angle. So far, when we left off on the previous conversation, we talked about how to convert angles from degrees to radians. We talked about earlier in last video how to represent and draw a whole bunch of different angles, but we had some common themes. We agreed in the very beginning of last video that our angles should always be starting by pointing eastward, and then they move in the counterclockwise fashion, and this is sort of what we agreed that we had to do. But that's not necessarily what we have to do all the time. For example, what we could do is, instead of moving counterclockwise, this is what occurred every time we had positive angles, we could choose to move in a clockwise fashion instead. We could rotate clockwise. However, the trade-off is, instead of having positive angles, we will now start having negative angles. And additionally, we might also recognize that if I start with a particular angle facing in the eastward direction, and I decide my objective is to somehow aim in this direction, there's no reason why I have to only turn a little bit. I could equivalently end up in the same position if, instead of turning a little bit, I decide to rotate once, twice, 3 times, and then end in that position. As long as I do that, I still end up pointing in the same direction, and therefore it can be thought of as the same angle. But of course, it was constructed in a different way. So of course, I have to somehow understand that these are different angles, but still the same angle. This is a relatively new idea for us, and we're going to have to give this notion a definition. The definition we're going to come up with is going to be referred to as coterminality. So what we say is, since 2 pi is, again, referred to as a full revolution, what we might recognize is that if our objective is to simply point in the same direction, if instead I decide to pivot and swivel around some number of full revolutions, but end up in the same place at the end of the day, these two angles are going to be coterminal. And of course, they're coterminal because they differ by only some number of full revolutions. To show you what I mean, let's take a look at an example. Here we have two angles, 17 pi over 6 and 5 pi over 6. For starters, I'm going to show that algebraically these are the same angles. So what that means is that they have to differ by a multiple of 2 pi. So what that means is that if I take, for example, theta minus alpha, that's 17 pi over 6 minus 5 pi over 6. That's the same as 12 pi over 6, which is, of course, 2 pi. So indeed, the difference between these two angles is a multiple of 2 pi. So equivalently, what that really means is that if I want to draw 17 pi over 6, it's equivalent to first draw 5 pi over 6 and then swivel 1 full revolution. That's what that means. So what this means graphically is that if I wanted to draw, say, alpha equal 5 pi over 6, it might look something like this. I'm going to start pointing in the eastward direction. I'm going to end up pointing somewhere over here. That's 5 pi over 6. And this is the angle in question. This is alpha, 5 pi over 6. Whereas, I'm going to use a slightly different color here. If I instead wanted to draw theta, which is 17 pi over 6, what this equation is telling me is that, yes, I'm going to end up pointing in the same direction, but I'm going to get there slightly different. What I'm going to do is I'm going to introduce a full revolution first. So again, starting in the eastward section here, I'm going to introduce a full revolution. Then, after I did my full revolution, I'm going to go 5 pi over 6. So after the full revolution, I'm going to do my 5 pi over 6. And then I'll still end up pointing in the same direction. That's the key. But the difference is I got there in a slightly different fashion. So the purple here is exactly theta. It's very, very important moving forward that you recognize that two coterminal angles, although they end up pointing in the same direction, they are not the same angle. What does that mean? This means, I'll write it over here, big key important part, theta does not equal alpha. They clearly can't equal because there's this 2 pi sort of that's keeping them from being equal. Coterminal angles are not equal. Let me write that down. Coterminal angles are not equal. They are, what we're going to now use this word, they are equivalent. In mathematics, there is a difference between two quantities being equal and two quantities being equivalent. Equal means you can literally bind them using an equal sign. Equivalent means they're kind of representing the same thing, but they're not exactly the same object. And so coterminal angles fit that bill. It's very important when you talk about coterminal angles to say what you mean what you say, and in particular, don't make statements like, these two coterminal angles are equal, because that's not mathematically true. So let's take a look at an example that somehow illustrates this in a little bit clearer of a fashion. Here we have an angle that's given to us, 17 pi over 3. We'd like to find a positive angle less than 2 pi, that is coterminal to it, as well as a negative angle greater than negative 2 pi, that is coterminal. The way to try to find coterminal angles is to simply start with what you're given and then add or subtract 2 pi over and over and over again until you end up getting something that you're looking for. So what we're going to write is we're going to consider a new angle. I have to give it a name, but I will not name it theta because theta is already a name in use. So there's a lot of options. You could pick a different Greek letter like alpha, or you could pick theta but give it a subscript. So maybe I'll consider theta 1. And this is going to be the given angle, 17 pi over 3. But instead, since this is a very large number, I'm going to go ahead and subtract off 2 pi. As soon as I do that, whatever this turns into will be coterminal by definition. And if it's positive, then I'll have satisfied my first answer. Well, when I simplify these two fractions, I'm going to end up with 17 minus 6 is 11 pi over 3. This is indeed positive, so we can give ourselves a check. This is positive, and it's not just positive. It's positive, comma, less than 2 pi, comma, coterminal to theta. That hits all the checkboxes. Now we want a coterminal angle that is negative, greater than negative 2 pi, and coterminal. Well, if we want it to be coterminal, what we can do is we can again consider, say, theta 2. Still has to be a different name. And what we're going to do is we're going to take, well, if 17 pi over 3 minus 2 pi was 11 pi, and that wasn't quite negative. Maybe what we can do is we can take the original angle, 17 pi over 3, and instead of subtracting off 1 full revolution, maybe instead we'll subtract off 2 full revolutions. This is 4 pi, and when I compute that difference, I'll end up with something like 5 pi over 3. This, however, is positive, and that's not a good thing, because that's not what we're looking for. We're looking for a negative angle. So this isn't a good thing to consider, but we're definitely getting smaller and smaller. 17 pi over 3 is a very large angle. 5 pi over 3 is a little bit smaller. So maybe our last consideration is instead we're going to consider theta 3, which is the original angle in question, but instead of subtracting off 2 full revolutions, instead we're going to subtract off, say, 3 full revolutions. When we do that, we'll indeed get, this is going to be negative pi over 3. So what we find here is that this number here is negative. It is negative, but also greater than negative 2 pi, and it is coterminal to theta. So that hits all the boxes. So indeed, what we found is we found two angles. One is theta 1. That is the first angle we were looking for, and then theta 3 is the second angle that we were looking for. Now, if I wanted to graph all of these, the fact that they're all coterminal will mean they'll all be pointing in the same direction. However, the amount of revolutions it takes to get there is going to be the key difference. So, for example, we might start by saying, okay, let's put theta 3 in purple. So this is going to be negative pi over 3. Pi over 3 is, again, 60 degrees, which is just shy of a quarter turn, but in particular it's negative. So what that means is that, again, I'm going to start in the positive x direction, but instead of going counterclockwise, I'm actually going to go clockwise, and I'm going to go just shy of a quarter turn, and this is going to be my angle theta 3, which is negative pi over 3. So the fact that I'm pointing in this direction, this is the final pointed direction. That's where all the angles are going to be looking. But the question is how many revolutions, and do they go clockwise or counterclockwise? So that's going to be the question to answer. So let's pick a different color. Maybe we'll pick orange. And we're going to label theta 1. This is 11 pi over 3. What we recognize here is that 11 pi over 3, again, we're going to be pointing in this direction. But since it's positive, we're going to be going in the counterclockwise direction. And this is going to be 1 full revolution along with a 5 pi over 3. Because you could rewrite this as 5 pi over 3 plus 2 pi. So this is going to be 5 pi over 3, which is this angle, along with a full revolution. So we're going to continue like that. This is going to be theta 1, which is 11 pi over 3. The last angle that we might want to draw is theta, which is going to be, maybe we'll put it in pink. Theta is 17 pi over 3, which, based on our math that we've done so far, we recognize that this can be rewritten as 5 pi over 3 plus 2 full revolutions. This is going to look a little bit messy, so maybe instead of drawing it on top of the one that's given, I'll draw a little mini version over here. What's going to happen here is we're going to start facing in that direction. We're going to have 2 full revolutions, 2 full revolutions, followed by 5 pi over 3, which is going to be just enough to bring us down here and point in that direction. So that's going to be theta. At the end of the day, all of these angles are pointed in the same direction. However, how we got there is different. That's what makes these angles coterminal, equivalent, and not equal. Now, there's a lot of angles in this world, and some are a little bit more commonplace than others. And so what we're going to do for the remainder of this lesson is we're going to talk about the most common angles you can run up against. So for example, we can start here with what looks like a pizza pie. And I've cut this pizza pie into 8 equal pieces. What that means is we have a variety of angles that we're witnessing. Again, if we start by pointing in the positive x-axis direction, this is where all angles begin their life. And then we rotate in a clockwise fashion. That is, we rotate in this way, right there. We're going to encounter angles as we swivel around this pizza. Of course, we might recognize that if we get to the first pizza slice, this is going to be, well, we cut our pizza, which was otherwise 360 degrees worth of pizza, and we cut that into 8 slices, so this is going to be 45 degrees. So this is 45 degrees. Similarly, however, you could have started in radians and said, okay, it's a full revolution, 2 pi divided by 8 slices, and that's going to be pi over 4. So 45 degrees is the same as pi over 4, and you might write it up there. We want to do the exact same thing, but for every single slice, noting that we have to do it referenced to starting on the positive x-axis. We have to start here. So if one slice got us 45 degrees or pi over 4, 2 slices is simply going to be double this. So one way you could think of that is that if we are taking a look at this angle right here, that angle is 2 times the one slice, which is 45 degrees. Of course, that's 90. Otherwise known as 2 times pi over 4, which is pi over 2. So this is going to be 90 degrees, otherwise known as pi over 2. But of course, we already knew that because this turn, right, the turn we just did is literally a quarter of the pizza. And when we computed this earlier, we simply took a full revolution, divided it by 4, and that's what got us 90 degrees and pi over 2. You can do and carry out this exact same process. And you could come up with, for example, what's going to happen over here. What's interesting is that there's a lot of ways you could do this. You could either take 3 pizza slices, you could take a quarter of the pizza and then add 1 slice, or you could take half the pizza and then subtract off a slice. All 3 of these are perfectly valid ways to compute this. So let's go ahead and tackle maybe that last option. Maybe I'll observe that this slice up here can be thought of as half a pizza minus a slice. So if half a pizza, we remember that's going to be pi, otherwise known as 180 degrees. We know that this angle can be thought of as half the pie, but minus a slice, where a slice is 45 degrees. And if you do the arithmetic, you get 135 degrees. Otherwise known as, if you did it in radians, you could do pi minus pi over 4, which then gives you 3 pi over 4. Whereas, for example, down here, you would then have, down here would be a half the pi plus a slice. So here you'd have half the pi plus a slice, which would be 5 pi over 4, otherwise known as 180 degrees plus 45 degrees. This would be 225 degrees. You can carry on in this fashion, and what you'll find is that if you have 3/4 of the pizza, this is known as 270 degrees, or 3 pi over 2. And then if you have all but one of the slices, this is 315 degrees and 7 pi over 4. And if you have the whole pizza, you come back here. Either you had none of the pizza, or you had the whole pizza. So that's 0 or 2 pi, otherwise known as 360 degrees. So this is a set of very common angles that we can run into. 45 degrees. This is a pizza slice that starts at 45 degrees, and then you can figure out, depending on how many slices of the pizza you have, what your total amount of pizza you have at the end of the day is. Of interest is that this isn't the only way to cut up a pizza. You know, if you have 8 people at a party, this might work. But, as we'll see in the next example, you may have to cut your pizza into, say, 12 equal pieces. Of course, if you start your angles at the positive x-axis and you take a look at what's going to happen for one pizza slice, this is going to be a full pizza's worth, 360 degrees, divided by 12 pizza slices. That's 30 degrees. Otherwise known as if you had 2 pi over 12, which is going to be pi over 6. So this angle, if you cut it up into 12 pieces, you would end up with either 30 degrees or pi over 6. And if you carry on in exactly the same fashion, what you'll end up finding is that if one pizza slice is 30 degrees, of course 2 pizza slices would be 60 degrees, 3 of them would be 90, then it would be 120, 150, then 180, then 210, 240, 270, 300, 330, and then 360. So the degrees are just adding multiples of 30 at every stage, whereas if you had to do it in radians, you would have to be adding pi over 6 every time. This is somehow a little bit more taxing, but not too bad. 60, for example, would then become pi over 3. We know 90. 90 is already pi over 2. 180, for example, is pi. And so if you want to know what the radians were for 150 or 120, you could just keep adding pi slices, or you could also think of it as a half a pi and then subtracting pi slices. So the 150 here could be thought of as half a pi minus a pi slice, which would turn into 5 pi over 6. 120 could be thought of as maybe a quarter of the pi plus a pi slice. And if you did that, you would end up with 2 pi over 3. And in exactly this way, you can proceed around the remainder of the pi, and you'll end up with, for example, 270 is 3 pi over 2. Something like 330 is the same as 2 pi, a full pi, minus pi over 6, which of course turns into 11 pi over 6. .300 degrees is the same as 5 pi over 3. 240 is the same as 4 pi over 3. And 210 is the same as 7 pi over 6. So these are, along with the cutting the pie into 8 slices, these degrees and radians are the other set of sort of classic angles that we have to commit to memory as we move forward. For those of you that are familiar with sort of the classic version of what a unit circle is, this might be more like what you think of. And this, I would highly recommend that we move away from memorizing a unit circle and we move toward understanding how these things are generated organically, so that if your memory fails you on the unit circle, you can then fall back on recreating it in exactly the way we just did. Now, the remainder of this handout has us take a look at these pie slices, but with the 8 cuts as well as the 12 cuts overlaid on the same thing, on the same unit circle. And what I'd like you to do is take the knowledge that we've developed so far, take a look at these pie slices. And for example, on this first one, whereas we knew that this angle right here was 30 degrees, otherwise known as pi over 6, for this circle, instead of using those, what I'd like you to do is I'd like you to write a coterminal angle for that pi slice that is greater than 2 pi. So in this case, instead of having 30 and pi over 6, maybe instead you consider 30 plus 360 degrees, which is 390. And instead of pi over 6, you consider pi over 6 plus 2 pi, which in this case is going to be 13 pi over 6. And I'd like you to do the same thing for every single angle found in this pi. That way we can get more comfortable with coterminal angles and how they're computed, where they're represented, and how they look graphically relative to one another. On the second pi slice we have down here, I would like you to do the exact same thing, but instead with angles that are negative. Still coterminal, but negative. So in that case, what you might have to do is take what would otherwise have been, for example, 45 degrees or pi over 4, and instead consider, say, 45 degrees minus 360 degrees, or otherwise known as pi over 4 minus 2 pi, which if you did it with this fraction world, you would end up with something like negative 7 pi over 4. So take a crack at that and see if you can't fill out the remainder of these circles. This is going to wrap up our introduction into trigonometry and our discussion on angle in radian measure. In the next video, we're going to talk about sections 4.2, 4.3, and 4.4. And in those sections, we're going to introduce trigonometric functions and try to understand what they are and how they're related to angles and what we talked about today. So until then, keep studying, keep up the good work, and I'll catch you all in the next one.